Hello there, Mr. Sutton here, bringing you the BC Calculus 8.3 Part 1 homework solutions on vectors. On this problem, we have the position of a particle given by this vector here. And let's see, y is a twice differentiable function of t. Good to know that, because they didn't tell us anything else about y. This is kind of weird, y of 2t. At time 1/2, we want the acceleration vector for our particle. Well, we've got position. That means we need to go two derivatives to get to acceleration. So let's start with derivative of 4t cubed. So this is going to be v we're figuring out here. So this is going to be 12t squared for that first component, for the basically x prime of t right here. And then this next one, I don't know what y really does, but I can sort of kind of use the chain rule on this. So this is going to be y prime of 2t times a tail of 2. So 2y prime of 2t. All right, let's keep going. And you'll notice in the answer choices, they haven't actually done anything with y other than double prime it. So this is definitely the right path we're going down on this. So for acceleration, we need the derivative of velocity. That's going to be, let's see, this first one is going to be 24t. And this next one, using the chain rule again, we've got 2y double prime of 2t times another tail of 2. So 4y double prime of 2t. And this is going to match which answer choice? Well, we don't know yet because they wanted the acceleration at time 1/2. So we actually have to plug in 1/2 to all of this stuff and figure out what that comes out to. So we've got 24 times 1/2, which is 12. And 4y double prime of essentially 1 here, which we can't really simplify any further. So 12 comma 4y double prime of 1 is going to be choice D. For this problem, we have the particle moving along the xy plane given by this vector here. This is the position. Always good to know what we're starting with. We want velocity vector at time 2. So we'll find the velocity vector in terms of t, and then we'll plug in 2 for t. So this is initially essentially like t to the -1 here. Taking the derivative of that to get v, the x part of v, the x prime here, this is going to be negative t to the -2. And then derivative of e to the 3t, that's e to the 3t times a tail of 3, so 3e to the 3t. All we have to do now is just plug in 2. So if we do that, -2 to the -2, that's coming out to -1/4. Over here, this is going to be 3e to the 6 if we simplify it. And let's see here, we got -1/4, 3e to the 6, that matches answer choice E. On this problem, they're telling us f is a vector-valued function, defined as f of t equals this stuff. They want f double prime of t. So this is a rare vector problem where they're not dealing with anything related to motion. This is just a straight-up function. But the idea is the same. You're essentially starting with position and finding the acceleration vector. So we need two derivatives of this thing. F prime of t, that's going to be negative e to the -t, comma, negative sine of t. And now f double prime of t, we just have to take derivative of each of these individually. So this becomes positive e to the -t again. And now this is going to be negative cosine of t. And that is going to match, let's see here, answer choice E. On this no calculator problem, we have a particle moving in the xy plane with these parametric equations. We want to know at which point the particle is at rest. So this one's going to take a little bit of work. At rest means x prime, and they only give us x here, so we'll have to find x prime, but we're saying x prime and y prime, our motion components, are both 0 if our particle's at rest. It has no horizontal or vertical motion. So we need to figure out those points and then plug them back in to get the actual x and y values. So let's start by figuring out what makes x prime 0. So let me write out x prime. That's going to be 3t squared minus 6t, and we want to know what values of t zero that out. So because this is not a calculator problem, I need to solve this by factoring here. I can take out a 3t, leaving me with t minus 2, and setting each of those equal to 0 and solving, I see that I have t values of 0 and 2, where x prime comes out to 0. So we can't automatically assume both of these points are going to give us an at-rest particle. In fact, we know they're not, because if you look at the answer choices, they each have only a single point in them. So that means only one of these must actually work. To figure out which one of it is, we're going to take a look at y prime and what makes that 0. So y prime in general is going to be 12 minus 6t. Now you could set this equal to 0 and solve, but I'm just going to plug both of these in because I don't really care if anything else makes y prime 0. We're just interested in the things that make both x and y prime 0. So y prime of 0, that's the easier one to test. 12 minus 0 essentially is just 12. Since that is not 0, we know our particle is not at rest at time 0. So by process of elimination, that means it better be at rest at time 2, but let's just plug it in to make sure. So y prime of 2, that's going to be 12 minus 6 times 2, so 12 minus 12, which is 0. So we know our particle is at rest at time 0. Now we actually have to plug 2, or this is time 2 actually. Now we have to plug 2 in to our x and y parametric functions to get the actual x and y values. So we need x of 2 comma y of 2. That's going to be, let's see, 2 cubed minus 3 times 2 squared, comma 12 times 2 minus 3 times 2 squared. So this is, let's see, 8 minus 12 is going to be negative 4. And over here we've got 24 minus, let's see, this is also 12, so that's going to be 12. Negative 4 comma 12 gives us choice A. On this problem, we have a particle with a position given by these parametric equations in vector form. We want to know in what direction our particle is passing as it moves through the point 3 comma negative 2. So this problem takes a few steps. If you want to know about direction, we're talking about whether or not x and y prime are positive or negative. And that means we're going to have to plug some t values into x prime and y prime. But we don't know the t value that we're going through this point at. So that's actually our first thing we need to do is figure out what t value we actually go through the point 3 comma negative 2. So in order to do this, we're figuring out what t value makes these things come out to 3 negative 2. Now you could do the x or the y. Between the two of these, it looks like the x is going to be a little bit easier to deal with. So I'm going to start by seeing where my x of t, 5 minus 2t in other words, takes on a value of 3. And if I get multiple t values, then I'll also figure out which ones make the y value negative 2. So solving this, we subtract 5 to get negative 2, divide by negative 2 to get 1. And just to double check, if you plug this back into the y component here, 1 squared minus 3 is negative 2. So this is the time that we need. We have to plug this time into x prime and y prime now to figure out whether those are positive or negative. X prime is given by negative 2, just a linear rule here. That means x prime of 1 is going to be negative 2. X prime of everything is negative 2. Since our x left-right component comes out negative, that means we must be moving left. So anything that doesn't have left in it can be eliminated. So really it's just down to choices A and B at this point. Next we check out y prime, which is just going to be 2t, so the derivative not too bad on this one. Plugging 1 into that, we've got 2 times 1, which is just 2. Significantly, this is a positive number. That means our up-down motion is positive, so we're going up. So left and up, which is going to be choice A. On this problem, we are given the x and y coordinates of some function on a plane curve parametrically. We want the acceleration vector at time 1. So we're going to come up with the velocity and the acceleration vector in terms of t, and then we'll go ahead and just plug 1 into the acceleration vector. So for x prime, that's the derivative of t cubed minus 1, or minus t rather. I have 3t squared minus 1. And then for the derivative for y prime, we've got 2t minus 1 cubed. That's going to become, using our chain rule here, 3 times something squared times a tail of 2. All right, let's go ahead and do the acceleration vector now. This first one is going to become 6t, that's x double prime. And for this next one here, we're going to use the chain rule again. So I've really got 6 times all this stuff squared. Multiplying by 2, that gets me 12, 12t minus 1. But then I have to multiply by the inner function's derivative as well. So that's another 2 getting multiplied out there. And at this point, I'm going to stop being lazy and clean this up a little bit. So this ends up being, we have a 6t and we have a, let's see, this is 24 times all this, so 48t minus 24. All right, time to plug in 1. So we've got 6 times 1 and 48 times 1 minus 24. That gives us 6 for the first piece of it, and there's only 2 answer choices that have that. And then we've got 48 minus 24, which is 24. So answer choice E. On this problem, I've got the position of a particle given by these parametric equations. We want the acceleration vector. So that means we need to take 2 derivatives and put them in a component form here. Let me start by getting my velocity vector. That's going to be x prime, which is 2t, comma, now we need y prime. That's going to be 1 over 2t plus 3 times a tail of 2. So we'll put a little 2 up here. So that's my velocity vector. I'm going to need to take the derivative of both of these components now. And in order to make this a little bit easier to deal with, I'm going to rewrite this y prime as 2 parentheses 2t plus 3 to the negative 1. All right, let me go ahead and find acceleration now. That's the derivative of these components, x double prime of t and y double prime of t. So we've got 2 instead of 2t. And this other one, we've got, let's see, negative 2 times 2t plus 3 time to the negative 2 times a tail of 2. So don't forget that. So this overall comes out to, let's see, this is going to be negative 4 over 2t plus 3 quantity squared. If I convert it into one of these, so that's going to be choice E then. On this problem, we have a velocity vector, and we want the acceleration vector. So this is a very quick, straightforward problem. You just need to take the derivative of x prime and y prime individually. So derivative of cosine of 2t, that's going to be negative 2 sine of 2t, using a little mini chain rule there. And derivative of e to the 3t, well, another chain rule. So we've got e to the 3t times that tail of 3, so 3e to the 3t. And that's going to match answer choice A. On this problem, we are given a position vector for some particle, and we want the velocity vector, but at exactly t equals 2. So we need to take the derivative of our position vector, the x and the y here, and then plug 2 into that. So taking the derivative of the x piece here, the ln of t squared plus 2t, this is ln of something, so we're going to use a chain rule. This is going to be 1 over the something, so 1 over t squared plus 2t. But now we're going to multiply by the derivative of t squared plus 2t. So that's going to end up in the numerator here because you're multiplying. So this will be 2t plus 2. And then we'll take the derivative of 2t squared over here. So our y prime down here is going to be 4t. All right, let's just go ahead and plug 2 into all of the t's. So taking care of this fraction here, we've got, let's see, 2 times 2 plus 2, that's going to be 6. Down here, we've got basically 4 plus 4, so that's 8. So 6 over 8, comma 8. And of course, we're going to have to reduce that to match an answer choice. So this will be 3/4, comma 8, which is going to give us answer choice A. For this problem, the position of a particle is given by these parametric equations. We want to know when this particle is resting. So we need to know basically when x prime and y prime both have a value of 0, at what t value that happens. Let's start by getting x prime and solving for all of this equals 0. So we've got 3t squared minus 6t. And again, we want to know where that equals 0. So we know where there's no horizontal movement. Factoring out of 3t, we have t minus 2 left inside. So that means t equals 0 or 2. Those are options for this. So these are places where there's no horizontal motion. But there might still be vertical motion, so we have to test both of these in the derivative of y. Let's find y prime and then plug some things in. So for y prime, I've got 6t squared minus 6t, using just my power rule here. And then this minus 12t becomes a minus 12. Let's plug 0 in. That's an easy one. So that's going to zero out everything with a t, leaving us with just negative 12. Now the important piece here is that this does not equal 0. That means that we do have some vertical motion, so the particle is not at rest at t equals 0. Well, that leaves only t equals 2. So at this point, since it's multiple choice, you could conclude 2 only is the correct answer choice. But let's test it out just to be sure. So y prime of 2, that's going to be 2 plugged into everything in my derivative right here. So this is going to be, let's see, 6 times 4 is 24, minus 12 is 12, minus another 12 is 0. Since y and x prime both equal 0 at time 2, that means the particle is indeed at rest at time 2. So that gives us enough to choose answer choice C.